Patkevich with the title Algebraic Understanding of Random System with Output. Presenter is Artyom Panchenko. So please start share your screen.
Of course, good morning. 1 second, I will start sharing.
Okay, it's almost good evening.
Oh, it's just a habit because I have
In
hope.
your text, it was written good morning. Yes.
Yeah. I believe you see my screen and
Yes. Yes.
okay,
Mhm.
we can start. Good day, everyone. Good day, dear colleges. My name is Artyom Panchenko. I'm from Kharkiv Karazin National University. It's a big honor for me to be here in a SETRI conference. Few words about me. You can find my ResearchGate account via the QR code if you want to discuss the researches or something like that. I have a degree of Magister of Computer Science in Vasily Nazarevich Karazin National University. Also, I have a degree of Master Engineer Informatique from Université Côte d'Azur, Nice, France. And my current position is PhD student in Department of Theoretical and Applied Information Science in Kharkiv Karazin National University. The research that I want to discuss here and present is it's co-algebraic understanding of random system with output. The two authors, me and my PhD supervisor, Professor Igor Shulkevich. First of all, we need to begin from the introduction, and it's obvious for today that we can't, because of technological limitation, we can't improve the single CPU unit computation power. So the one way to increase the computation power of a system, computer system, is to design it in a distributed approach. For us, distributed system, it's a set of independent entities that works in a cooperation and solves the problems that cannot be individually solved. Uh, in this current research, we focus on cyber-physical system. It's some kind of hybrid of physical component and cybernetic components. It's really mainstream technology for today. It's widely used in Internet of Things and some like it stuff. And modern world dictates us requirements, and the system should have intelligence. Of course, it's we understand it as a system make decision based on accumulated information without any interaction with some kind of human or yes. When we design the cyber physical system, we always will face some problems. And the main of them is we have high requirements for reliability of the system. Of course, it depends on the domain, and but if we talk about the cyber physical systems that control the traffic lines, lights, or something like that, the unforeseen situation can emerge, and it, of course, it will lead to system failure, and the consequences of this emergence can be catastrophic. And if we talk about the traffic line, for example, the catastrophic, it's a car accident, and some people can die because of it. So we have very high requirements for reliability. In Kharkiv Horizon National University, we have a set of papers, scientific papers related to this topic. Of course, I called it a project. There are around 10 researchers. Some goals were achieved. You see it on the screen. It's understanding safety constraints co-algebraically, understanding clock constraints co-algebraically, and co-algebraic approach to studying discrete system with output, the general undistributed case. You can find this papers in the internet, very easy, or in ResearchGate if you are interested in it. The goal of my current research is false. In the state of the art that I discussed before, they designed the cyber physical system as completely deterministic. So, but we understand that the system should work in real-time mode. So, deterministic approaches doesn't make any sense in this case because it's impossible to collect the information about the system if it's very big. So it's necessary for us to introduce a random approach or statistical, stochastic approach. In this case, I believe that there are no difference. It's the same words. And we need to model the probability in this paradigm of co-algebraic approach because this research is a part of the project that I discussed. Before we start discussing the current research, I believe we need to make some kind of preliminaries of algebra, and we start from the definition. In the screen, you see two definitions of the algebra, and first we used in the paper. It's more formal. I will use this notation in the slide, so it's a reason why we need to discuss it. We need to see it. We will call the carrier of some system as A underlined, but to discuss the algebra, I believe the better will be to discuss the second one definition. So we have some functor f from category C to itself, and f algebra is just a pair of some kind of object A, very abstract object, and the arrow alpha, such from A to F applied to A. From the definition, we see that it's a really good model to modeling the dynamic function, dynamic system, sorry. And in this case, the f, it's a dynamic function that change something very abstract object A, the transform it. The second one, very important definition in algebra is a morphism. Sorry. I need to be completely. So the morphism is some kind of technology that you can see the definition on the screen. It's very simple definition. It's just an arrow from carrier A to carrier B, and it's a morphism if this diagram commutes. So there are no anything difficult to understand, but for us, we will understand this as a technology to expand our theory for domain A to domain B. For example, we know how to perform addition for natural numbers, and we also should know how to perform the addition for the integer numbers, because both of them numbers. And with a morphism, with this technology of morphism, we can expand our theory from one domain to the second one. This slide is about some kind of notation propositions that we use in the paper, and I will use it in the slides. With a morphism, we create not just a one coalgebra, but a class of coalgebras, because we can expand our theory and some kind of move from one domain to other one with these arrows. So it's just a class of coalgebras, and we will denote it as clog F. It's some kind of just notation proposition. The last, but is for me the main, the most important definition from the algebra preliminaries. It's a final algebra. Very similar to the morphism, but in this case we have only one possible error f, so it's some kind of terminal object in the class of algebra f. I believe it will be more clear in an example. The example is really classical for the algebras. It's a dynamic system. It's where we have the x is a set of states of this system. So dx equal x, it means that our dynamical system, our transition in this dynamical system will not change the set of states. And df equals f is just a mapping between some kind of set x of state of some certain system and the y set of states in the second one. It's a different system, but we understand that we can create the mapping between the system states. You see the morphism in this picture. Of course, here we have a final system. It's very obvious to get the terminal object in this case, but actually to prove that, I believe I need more than half an hour and maybe even more than an hour. It's very complicated process to prove that this system is a final one. But here it's obvious because it's very simple example. We understand the terminal case here. It's a dynamical system with only one state, with only one possible state. It's one. We understand that in this system we have only one transition function. It's a dynamic function. It's just an identification of this state. Why this example is important for us? Because by this example, we understand that the final algebra is primarily a tool for maximizing the generalization of the model. So we have some model A, model B, they have some their own behavior. But final algebra object, it's a system that does not carry any the systems that have only general behavior of this category of system. Of course, in this example, the final algebra is not interesting for us. It's not interesting for research because it's very obvious. But it's just an example to get what is algebra, what is final algebra, and why we use it. I believe it's became more clear for you. I want to end the introduction part with a quote of Bart Jacobs. It's maybe the main algebra influencer in modern world. It's a quote from his book. He says that algebra illustrates the change of entity under the influence of transformation. So it's completely that we see from the slides that we have some abstract entity, we have some abstract transformation, and algebra show it. As you remember, the goal of the current research is to introduce a random approach for design the system with output. First of all, we need to define the distribution of the functor, of course, and we use G-remonad here, and it's really easy, really simple actually, not easy. Distribution and the functor here is just a function that provide for each set from X category of category of states number from in interval from 0 to 1. It's a probability that this state will occurs. And we also add some kind of requirements to be sure that this distribution is really probability distribution. So probability should not be equal 0, and the sum of probability should be equal 1. Very simple. Of course, here we have a morphism from this and the functor. For any mappings f such from x to y, we can define the morphism. It's very formal morphism here. It's lambda p lambda y from y, sum x from x, fx equals y, p from x. Mainly, it will take into account following in order to obtain the probability of occurrence of a state y of states of from set of states y from some system y. It is necessary to add up of probabilities of the states corresponding to the states from a set x. As you remember, with a morphism, we create a mapping between the states from X system and Y system. We have two different systems. And if we have from the state, for the state Y, we have a lot of corresponding mapped states from states at X, we just sum their probabilities. A lot of state word in this definition, in this explanation, but it's a formal math. We don't have any other way. System with output, we use that definition in the previous researches. It's some kind of Sn coalgebra equals n multiplied by x, and SF morphism, it's IDN multiplied by f. What does it mean? We have some state set x of system states, and we have elements that are notifications. So for each state, we have notification. Of course, for different states, we can have the same notification. So it's just very simple. To introduce a random system, we use the same definition, but we only applied the distribution and the function here. So we have now that it's d applied to n multiplied by x and d applied to idn multiplied by f. With that stuff, we create the probability distribution of the pairs, state, and notifications. So with that, with mapping and with morphism and the objective, we can define the coalgebra with of random system with output. It's a mapping sigma. We call it sigma. From x to Rnx, it's below called random system with output. In this case, set x called the carrier and denoted as denoted by sigma underlined. We'll use this notation in the slides, and we'll use it in the paper. The first example of a system like that I want to introduce, it's tree. We'll denote it Tn. It's a set of infinite trees such that each node had the most infinite children. So the only finite states or finite number of children for each node. Each node executed the root node is delayed the element of n. So only the node in the first level doesn't have any notification because it's some kind of program start point. And each age is labeled by transition probability. So it's very simple to get that it's just some kind of example of system with output, but only in tree view. Note that each subtree of a tree, it's specified kind is a tree of this kind. So each subtree can be have the same behavior that all that big tree. Here, if we will raise the variable of this root. This node lead us to the definition of the system. It's mu. We denote it as mu such from Tn to Rntn. It's very similar to fractal theory. So each subtree have the same behavior structure as a big tree. Here we want to discuss how we can get and how we can create the subtrees. Not create, but restore the big tree from subtrees. We can use the following distribution. It's mu t equals sum of probabilities that the next state occurring with some kind of function delta that provide us with a notification. And easy to understand that MT really restoring uniquely big tree T by following it restore tree Ti for I equals 1 to K1 by labeling it as it's with root N1I. We create a new root with that, and we create the age from the new root to the root Ti and label it with the probability P1I. We see it on the screen on the image. It's a little bit formal, I agree with you, but it's correct. You can find more details and proofs of these statements in the paper. It's very big to put it into the slides. For random system with output, we define the morphism as false. It's means the probability of fx. Of course, fx here it's a mapping between states from x set to states from y set. So probability of transaction from fx to y with notification n and system tau equals to sum of corresponding probability from system sigma from x to x point. it's the same morphism that we discussed in distribution and the functor, but the notation, as for me, it's more clear. Let's go forward. Oh, of course, with that stuff, with the morphism and objective, we can denote the category of morphism, Rn morphism, and we will Rn coalgebras, sorry, and we define it as a coalg Rn. The second one example shows us how we can create the morphism between the trees. So we have a tree from a system X and we have a tree from a system Y. Here it's a system sigma and system, no, it's X and Y, sorry about that. So therefore, step to perform this morphism, we have a set of children for root is formed by pairs N, Y, and from N it's identification. Such that sigma x to ny bigger than 0, more than 0, it's a distribution, probability distribution requirement. So we don't put here the nodes that we can't reach. So it's not make any sense. Node ny is labeled with n with the same label that corresponding state from x system. The edge connected the root and node ny is labeled with the sigma x and y. It's we use a distribution and the functor here, morphism for distribution and the functor to get the edge, the probability to get this state in y system, and then this process is repeated for each node and y using y instead of x. So its example show us how we can perform the morphism between the trees. And in this step, we can some conjecture that it is evident that the tree chi sigma x that I showed to you in the previous slide meets all constraints characterizing trees from Tn. Moreover, we have a morphism here. It's a really morphism by construction of k sigma. The constructed bow random system with output mu is a final random system with output, and the constructed family of Rn morphism chi sigma such from sigma to mu is a family of anamorphism. Yeah, we have a conjecture that this tree structure it's a terminal object of this set of coalgebras, but unfortunately we don't have a proof in the paper. So for the conclusion, the study of the category of Rn coalgebras is interested in the context of constructing semantic models, of course, and we can solve the problem of impossibility to full determinacy of a system occurs in cyber physical system with introduction of the random system with output model. And of course, because we don't have proofs of our conjecture, we have a point to the further research. First of all, we need to develop the formal technique for specifying and analyzing the final random system with output. We need to prove this conjecture that we have, because it's looks like it's clear, but it's not very easy to prove that stuff. To construct an analogy functor as a tool for studying safety and causality constraints by joining system with output and a detector, and to construct the random analogy of a system with a termination for defining the indicators of system failures. These 2 points is related to the project that I introduced to you in the third slide, as I remember, or fourth. And we need to extend the technique being developed to discrete distributed system for the analysis of causality relations based on the logical clock model. It's also related to the project that we have in Kharkiv as a national university. So this current research should be expand the series that was developed when team worked on this project. That's all from my side that I want to share with you my research, and I believe we can start the questions and answer session if you have any questions.
Thank you for your presentation. Questions, please. I have a question, Artyom. At the beginning of your talk, you said that you consider discrete systems, but there are continuous components like time, maybe some others. So what is the relation between discrete components and continuous components in your research?
I clearly get your question, I will show the slide. I believe it was question to this slide, clock constraint algebra.
Maybe. So what you see, discrete system with output, yes?
Yeah.
But you have also continuous components like time, for example, in your system.
In
On
our
some other slide, you wrote that time is continuous, real time.
Yeah, I get your question. It's a good question, I believe. When we work with a distributed system, when it's really distributed, we can't work with the real time. Only models that we can use here is a model that was provided by Leslie Lampard. It's a model of logical clocks. So we don't have any interaction with some continuous or some real time as we understand it as humans. It's, minutes, seconds, hours, extra. We work with causality constraints. So something will be occurred only if something will be occurred. So A moment will be only after the B moment. And that's all. In distributed system, we don't use any real time. As I as I said this in real time mode, I mean that just right now we need the result right now of this system work. We because I don't need the traffic light control decision tomorrow. I need it right now. But when we design the discrete system, we work only with logical clocks, not with real clocks as we humans understand it. I believe I answered.
Okay, thank you.
Thank you.
Do we have questions? No questions, yes? Okay, it's just time to start the next talk by Tatiana Ryzhenko, Sergei Zgadov, under the title Computer Simulation of the Completeness and Motivation Level in the Context of Student-Tutor Interaction. Presenter is Tatiana Ryzhenko. So I have a floor, please start.
Yes. 1 second. The topic of my representation, computer simulation of the competency and motivation levels in the context of student-tutor interaction. The person enriched with knowledge only then with knowledge something means to him. One of tasks of school to teacher object on such interesting and life form that the child most wanted to study them and remember. Studying only according to books and my means of conversation is quite limited. Amongst modern methods of search of pedagogical systems, special position is held by methods of mathematical and simulation, computer modeling. This means that the real pedagogical system is replaced with abstract model. Some idealized object has the most essential properties of the studied systems. At the same time, the behavior of model is investigated by using mathematical methods and by computer simulation. The last means that the creation 1 second, please. The last means that the creation of the computer program with because like the teacher pupils system and conductions the series of examples at different parameters, initial conditions and external influences. The high speed of modern personal computers allows you to process large amounts of information and quickly carry out computer simulation. Sharing the initial data and model parameters make possible to investigate ways of development of systems to define its status at the end training. This is the advantage of this approach in comparison with the methods of qualitative analysis. The computer models considered in the present work can be used when carrying out of a pedagogical experiment is impossible of result or negative.
Sorry, Tatiana. Okay.
Also, next. The purpose of the work of the mathematical descriptions or the process of teaching students, taking into account such parameters as the level of competences, the level of motivation, the level of perception of the material. The method of random numbers is used for the evolution parameters in time, as well as hypothesis about the dependence of the growth of competency on other parameters. Let us consider the continuous model of training consisting of one component model of training, multi-component model of training, and the generalized training model. Mayer formulated the principle with are the basis for one component model of training. With this problem statement. Sorry. What was this? This Mayer formulas as generalized training. Yes, information, knowledge of given peoples is get of equal elements. All elements of training material are equally easily remembered, and with indication speed are forgotten. Process of training summed down to assimilation of knowledge and lasting speed of change of amount of knowledge is equal to the assimilation speed sum. Time of assimilation of the elements of training material is much less the duration of training. Speed of increase is knowledge is proportional to the work of level of knowledge of the people and the motivation. What is the more the people knows, the easier they already available. On the other hand, the motivation of the people, if the less efforts is lower, he spent and the speed of increase is in knowledge is lower. Problem statement. Problem statement is a mathematical description of the process of teaching students, taking into account such parameters as the level of competence, in the level of motivation, the level of perception of the material, and take in account the parameters and properties of students are random. Indefinitely identify the role of the tutor of the educational process through these model properties. Next slide. Information model. We have two objects, student and teacher. Tutor this mode of teach delta M. Set of students represent a classroom. The teacher is charged by the degree of motivation influence delta M and portion of information delta E per unit of time. Each student is charged by a level of competency, motivation, and level of represent A. Which charges mental abilities of the student and considers loss of information for forgetting. It is also necessary to charge mass influence of the teacher. During the learning process, the teacher influences the S, C, and M parameter of each student regularly. Next. They made the assumption that the growth of competence DC at each stage is definitely proportional to the current competence of the student and this motivation. Process of training is assumed to be broken into the get of small stages on each of which assessment of competence is possible. Daily assessment of independent work of the student of test results can be such a stage. At this stage, we will assume that this assessment is subjective. Also, we will consider that the motivation of the student changes depending on many factors. Thus, they assumed that the motivation of student depends of many factors, and it can fluctuate in a random way. Nevertheless, the role of the teachers is a defining factor of change of motivation. Therefore, the model considers influence of the teacher on motivation, increases of reduces, and how strong. Consequently, we will consider that its challenges acidity on normal distribution with dispensative half delta M, half of delta and medial delta M. Here are the steps in the algorithm based on the formula in the previous slide. The M0, C0, A parameters for students are get accidentally. where Gauss delta m delta half of delta m. This normally distributed Presidalum number with medial delta m and dispersion half of delta m. T and T charge from 0 to T. For each student, decide the founded equation provided on the slide on the program of the screen. Next. Interface of the program of modeling. Let's take value on influence on motivation, and we reserve the diagram the dispensers of change of competence of group of students from time. It is considered initial parameters of students, allegory, variable, and influence of students of each other. It's not considered. Sorry. Let's consider the different result. Echoes of height motivation. We will consider it on slide 8. Let's take value of confidence of motivation 0.5, and we will see that in most cases sharp gain even at the average level of students. Let's increase motivation confidence to 1, and that is twice. We saw that desire studies leads to gain of competence even at the weakest. Truth, they grow consolation that influences of motivation is not accidental here. Now they will consider it the motivation cause. Is it a cause which represents the greatest interest? Is as it is difficult for high motivation of students to reach. Happens much more often but the teacher make mistakes at simply of material, and students begin to lose interest regularly. I pay your attention that the teacher carries out the role and given a portion of information, but it does choose that interest of at students regularly falls. Let's consider it a cause of an easy demotivation. Let's set delta m minus month null that's 5. Students here slightly miss, but nevertheless study something, but the trend was already outlined. We observed regress of the strong students, and we do not observe gain in other cases. We see that most of students begin to lose the competences of if they test them. We will see the deterioration of progress by the end of equational process. The truth of stream of student due their personal qualities shot a little ahead, but not much more. It were the strongest students. By the way, parameter delta E was same is both cases. Influences of the training program was not the disservice as the motivation role. It is represented an obvious output. Obvious output, but look, this form is diagrams. We do not know what they were trained by teacher in, but they can understand the trade progress, whether the teacher motivation them or not. The fact that they can judge quality of teaching is an unvariant consequences. Whether knowing anything about the maintenance of a course, nothing, only dynamics of progress. If we of course can adequately estimate competence of progress. It's, by the way, a subject for a separate research. Future direction of research, it's a solution of the return task search, maybe results of regular testing. Extrapolation of education process, use of bias approach, and probabilistic assessment of competence, development of technique of estimation of competence, research of students' motivation factors. Output is points. We see as it is important to evaluate parameters, that is to solve the return problem account to a result of teaching, to calculate teaching parameter. It is possible to try will predict what futures development of competence of student of the basic of result of the previous testing. Probabilistic approach will be win that we will try to predict with that probability the student will be highly appreciated at the following testing, knowing its preview result. At the same time, sometime it's possible already to try to predict this probability instead of competence. Having connected this value somehow, for example, having solved the assumption that they are directly proportional. Problem of estimation of competence. It's what we subject estimate competence, and perhaps Bayesian approach of it can help in, and also is necessary to study / work teacher of drawing up test as I will repaired competence not difficultly missing value. They can evaluate it by result of testing that is indirectly. Are any other factors in increasing on the student motivation? How to motivation student to learn? That is all. Thank you for your attention.
Thank you for your presentation. Let's go to questions. I see a question by Vitaly. Vitaly, will you ask him yourself a question?
Thank you for your proposal. Yes, I can ask. So thank you also for your presentation. And I would like to know how did you measure variables of your mathematical model, such as motivation, perception, competences, because you indicated about probabilistic approach which you used in your model, but you don't expand it to all variables on your slide. Please explain this moment.
Прояснить переменные, как ты измеряла. I used. Competence is proportional. I use linear scale.
I use a linear scale for a variable.
Competence is proportional.
Competence proportional
To student testing.
to student testing results.
Maybe I can ask in another way. Did you generate these numbers? For example, it's artificial data or it's experimental data in your research?
Numerical experimental results.
It's
numerical
experimental result.
So you generated this data and it's not a real student. It's only some hypothesis about this data.
Yes.
Okay, thank you.
Thank you.
Okay, more questions?
Can I ask my question
Yes,
in
for sure.
Ukrainian or Russian or some language that will be more
In English.
Okay.
Official
yes.
policy is English, yes.
Okay, got it. Which kind of algorithm do you use? Is it something very similar to like in machine learning, or it's this algorithm was designed by you all, or it's some kind of algorithms that you reuse to solve this problem?
It's consumed algorithm
of Runge. It's about how.
If Sergey is present, maybe he as a co-author can answer questions.
Yes, I am.
Yes, please answer. It will be more understandable for us.
Yes, the question about model is I describe more clearly. In this model, we used our algorithm that is near to algorithm of solving differential equations. Says algorithm Runge-Kute, and its algorithm was described on the slide with some difference that the growth of delta m is pseudo-random on some normal dispersion.
Artyom, are you satisfied with
Yeah,
that?
I got it. Thanks.
Okay, I also have a question. On one of the first slides, it was written information and then knowledge in the parentheses. Does it mean that you consider the information and knowledge as synonyms? Or in your model, you have some difference between information and knowledge?
We make difference between information and knowledge. We concern that portion of information leads to growth of knowledge at every stage of educational process.
But the question is, what is knowledge? You just say that when you have more information, you have more knowledge. It's again just the same information and knowledge. Or information you consider only basic elements.
No, information and knowledge is different things. The information is the reason or ground of knowledge growth. So we think that acceptance of portion of information on our model leads proportionally, and this emphasized by Meyer leads to growth of competence of knowledge. In our model, we difference these terms.
Yes, but you see, knowledge, of course, it's much more difficult than simple information. For example, if you add new contradictory information to the information you have earlier, non-monotone, so to say, reasoning, your knowledge may decrease, not increase.
Yes, we think that that is a fact that in some case the portion of information, and we show in our numeric experiment, do not lead to increase competence because motivation is low, and the student couldn't accept this information and worked out knowledge on it.
Okay, let me make a small comment. It seems to me that educational process is very difficult and includes such aspects as motivation, perception, competence, knowledge, wisdom, etc. But your model is based primarily on the notion of information, and it is, let me say, monotone model because you appeal all the time. If you have more information, then you have more knowledge, more competences, and so on. So I propose in the future papers to write more precisely that model reflects only part of the process. Because when you wrote the mathematical model of educational process, we do not believe this.
So, thank you.
Okay. Does anybody have questions? No, then I would like to thank the speakers, all participants, for presenting their papers and to their attention to the talks. I invite you to further sessions of ICTERI and for participation in the next ICTERI 2023. Then goodbye to everybody. Let's meet on other sessions.
Thank you.
Yes, goodbye to
Bye.
Thank you so much.
thank you.
Thank you so much.
Yes, I have one more session. Goodbye.
Sorry.